Okay, another integration by parts, but this time we will do it where we have to evaluate. So we'll look at the integral from 0 to pi over 4 of x times tangent squared x dx. So I'll do another example a little later, but one way to handle the fact that we have to do this that we need to actually compute this, evaluate this integral at the value 0 and pi over 4 is actually just to forget that for now and just do this as we would any of our other examples of integration by parts without limits of integration. We'll find an antiderivative and then use that to compute this at the end. So I'm gonna focus on this problem first. This is kind of a rough integral to take, and so I don't want to really worry about too many things at once. So forget the limits at the moment. So we will use integration by parts on this, and this one's not so obvious. After some trial and error, there's actually a trigonometric substitution we're going to make here. So I'll remind us of that up here. Hopefully we all remember sine squared x plus cosine squared x equals 1. If we divide everything there by cosine squared, we get tangent squared x plus 1 equals secant squared x, or tangent squared x equals secant squared x minus 1. Okay, so this is what I want to replace tangent squared with. The reason being, tangent squared is not an easy thing to deal with. I don't have an antiderivative for it, and it's not an obvious thing to deal with. However, in this form, we might notice or recall from Calc 1 that secant squared x is the derivative of tangent. Okay, so that's going to come into play in a second. So let's rewrite this this integral with this substitution. Secant squared x minus 1 dx, right? So these are equivalent expressions, so I've substituted one for the other. So now I'm going to try parts on this. U is going to be x, du will be dx, dv will be secant squared x minus 1 dx, and v is then tangent of x minus x. Right, so just if you don't remember this one, you can look it up, or you can use the quotient rule if you remember that tangent is sine over cosine of x. When you do the tangent, the quotient rule, you find that the derivative of tangent x is secant squared, and then of course the derivative of negative x is negative 1. All right, so let's see what this does for us. Put this into our parts definition. We get u times v, so x times the tangent of x minus x, minus the integral of v du. Right, so this will be tangent of x minus x dx. Okay, so this part is done. We still have to evaluate, but as far as the antiderivative goes, we need to compute this part. So let's now concentrate on this part. So let me look at tangent of x minus x dx. This is tangent of x dx minus x, the integral of x dx. This one's pretty simple to do. Tangent of x dx minus 1/2 x squared. I'm gonna ignore constants of integration because I know at the end I'm going to be evaluating this, and when we evaluate it, those constants disappear anyhow. Okay, so now we've gotten this part out of the integral. We've got one more piece left to do. Okay, so now I'm going to just concentrate on tangent of x. We've done this one before. We actually did this when we did u substitution. if I rewrite tangent as sine of x over cosine of x, we can use, let's use t, since u already means something in this problem. Let's take t to be cosine of x. So then dt equals negative sine x dx, or negative dt equals sine x dx. So then this integral becomes, we pick up a negative that I'll put out front. Let's see. We've got sine x dx is our dt, and we've got cosine x is t. So negative the integral, or the antiderivative of dt over t, or 1 over t dt, which gives us negative natural log of the absolute value of t. Again, I'm ignoring my limits of integration, constants of integration, because we're going to be evaluating this. And then I need to substitute this back in. T is cosine, so this is negative natural log of cosine of x. Okay, so now we need to go collect everything. All right, so let's do it this way. So we are trying to find x tangent squared x dx. We had first found that it was x times tangent of x minus x. That was the first piece of this. Then we needed to find this derivative. So we'll have minus what we found for the tangent of x minus x derivative. And we have two parts to it. We have a negative natural log of cosine of x. So we'll end up with a positive natural log cosine of x, absolute value of cosine of x. And we had a negative 1/2 x squared, so that will also become positive, plus 1/2 x squared. Okay, so there's our antiderivative without the constant of integration, because remember, originally we wanted to oh, sorry, I thought I saw a mistake. I realized what I was thinking. Sorry about that. Originally, we wanted to evaluate this at 0 and pi over 4. So now let's do that, right? So when let's just write those evaluations in here, right? Then we know we have to evaluate this whole thing between 0 and pi over 4. So let's do that here. Putting in 0, pi over 4, I'll have pi over 4 times the tangent of pi over 4 minus pi over 4 plus the natural log of cosine of pi over 4 plus 1/2 pi over 4 squared minus, now we're putting in 0. When I put 0 in for x, it multiplies to this, that all goes away. Cosine of 0 is 1. Natural log of 1 is 0, so that term goes away and this term goes away. So actually, there's nothing to subtract. When we get 0, it's all 0. And so we just need to evaluate. Pi over 4, the tangent of pi over 4 is 1. Cosine of pi over 4 is root 2 over 2. And then we'll have, let's see, pi over 4 squared will give me pi squared over 16, and then I'll multiply by that 2 to give me 32. And this is a perfectly reasonable way to do it. There's some factoring. I don't know that anything would give us a much clearer version of this. And so this number is the number we're getting.